Welcome back to the 13th part of Debugging at Scale, where we've dealt with all these bugs in the past and can share the experience. Through decades of programming, the bugs that we deal with remain similar, regardless of operating system, language, through mobile, desktop, and server. There are some issues that aren't as common or changed significantly. Memory leaks are vastly different thanks to garbage collectors. Memory corruption is rarely an issue in managed languages. Concurrency issues are a mixed bag. Managed languages made threading issues more predictable for most parts. Asynchronous tools, such as promises, shifted some of the burden. But with these APIs, process scale became a big issue. When we have multiple concurrent containers working on the same data, concurrency problems are often harder to debug than localized threading issues. The vast majority of bugs we deal with on a daily basis are related to the wrong application state. Second to that are exceptions and faults. Concurrency related issues are often the hardest to reproduce and fix, but for most systems, they're relatively rare. Exception-related failures are relatively easy to detect. You usually get a stack trace directly to the error, together with a description. We can place a breakpoint on all exceptions and verify that nothing fishy is happening behind the scenes in one of the methods. Exceptions are loud and obvious, so unless someone silently catches an exception, which happens, we can track the root issue relatively easily. I would also strongly recommend a linter rule that checks against swallowed or unlogged exceptions. Linters are tools that review your application code for common bugs and pitfalls. I highly recommend adding one to your continuous integration process. Checkstyle is a common cross-language linter. It supports a check that blocks empty catch blocks. It still can't block stupid code. That does nothing in that block. But it's a start. Faults are standard in some languages, but can also occur in managed languages where the VM crashes. They are usually coupled with a core dump that we can open in the debugger to investigate. Platforms like Java also include the full state of all threads in case of a fault. This can point us to a VM bug or an issue in a native library. It's very important to collect this information and analyze these crashes. Sometimes a small change, such as a minor JVM version upgrade, can resolve such crashes. Getting core dumps working on all OSs is tedious, so I would recommend checking out Oracle's documentation on the subject. Notice that this is specific to the JVM, but many of the concepts apply universally. Once we have a core file, we can open it with most native OS debuggers and inspect the stack trace of the crash. Sometimes runtimes such as the JVM can include tools such as JHSDB, which we can use from the command line or using a GUI. I will discuss JHSDB in the next module. Threads are a source of difficult bugs, yet most bugs result from bad application state. To track state-related issues, try separating the state elements that are modified concurrently and the state that's read by the problematic block of code. Assuming you can, try overriding the variable value within your breakpoint by setting it during debugging. You can set variable values in the watch area or via the expression options in the debugger. This is a great capability that most developers don't utilize often enough. If you're able to narrow down the value of a specific variable as the cause of a problem, you're already well on your way to solving the problem. If this isn't helping, try identifying specific fields that might be problematic. You can use a field watch point, which I discussed before, to track changes to state and even value reads. If the problem persists, a powerful approach is returning a hard-coded state or a state from a working case. I'm normally not a fan of techniques that require code changes for debugging since I consider the two distinct tasks. However, if you're out of options, this might be your only recourse. The memory debugging capabilities and object inspection capabilities we discussed before are also very helpful in these cases. A very common bug is a case where a copy of an object is made with slight modifications. Both objects appear identical to the casual observer, and as we debug, we might get subtle failures as a result. Back in the days of JPA, which is Java Persistence Architecture, I used to do quite a lot of consulting, and there was a common bug that was caused because developers implemented equals and hash code correctly, at least in terms of Java coding conventions. The problem is JPA has some problematic edge cases. This created a situation where the object identity changed between its unsaved and its saved state, causing some issues. Specifically, the object ID will be null in the unsaved state, and it will have a value in the database, return return the identity. As a result, we sometimes had two entity instances in RAM, and it was very hard to track such issues. Thread problems have the reputation of issues that are hard to solve. As I said before, that reputation isn't always justified. The easiest way to check for threading issues is, as I mentioned before, logging your current thread and or stack. Do that in the block of code that's causing the issue. Then add a similar trace point on fields used by the block of code. Thread violations should be pretty clear in the logs. Using marker objects to keep track of various threads is also a powerful tool. With threading issues, the key challenge is reproducing them consistently. Creating a massively threaded unit test is often the most powerful debugging tool you can have in your corner. Notice that you should probably avoid Java's virtual threads in tests as they might skew the results. If the problem is a deadlock, then you're probably in luck, as those are usually pretty clear once reproduced. The app gets stuck. You press pause, and the debugger shows you which thread is stuck, waiting for which monitor. Monitors are OS-level primitives that block a thread from entering a code block, roughly mapping to Java SE synchronized keyword. You can then review the other threads and see who's holding the monitor. Fixing this might be tricky, but the debugger tells us what's going on. With a live lock, we hold one monitor and need another. Another thread is holding the other monitor and needs the monitor. A live lock can result in a deadlock. Unlike a deadlock, a live lock can occur while threads are still functioning. It can seem that both threads are working correctly and aren't stuck, because live locks can occur with live threads. The code might appear fine on the surface without a clear monitor in the stack traces. Debugging this requires stepping over the threads one at a time in the thread view and reviewing each one to see if it's waiting for a potentially contested resource. It isn't hard on a technical level, but it's very tedious. That's why I recommend enabling thread groups in the thread view. A typical application has many threads, which can make this hard to follow. This produces a lot of noise, which can be reduced by grouping threads and focusing on the important parts. Again, logging using trace points can be very helpful in these situations. This is one of those elusive bugs, such as race conditions, which are often classified as thread problems, which they are. But during debugging session, it's often easier to see them as a separate task. Timing issues and race conditions often occur when your code has some unintentional reliance on performance or timing. The way I approach race conditions in threading code is this: it's a state bug. It's always a state bug. When we have a race condition, it means we either read from the state when it wasn't ready or wrote to the state too late or early. Field watch points are your friends in this case and can really help you get the full picture of what's going on. You can also simulate bad state situations by changing variable values. I suggest creating field watch points with conditions related to the current thread. This way, they will trigger if the wrong thread tries to access a field that it shouldn't. Performance problems caused by monitor contention are harder to track with a debugger. I normally recommend randomly pausing the code and reviewing the running threads in your application. Is ThreadX constantly holding the monitor? Maybe there is a problem there. There are some system tools such as strace and dtrace which can be used to track overuse of monitors. We can derive assumptions and prove them by logging the entry and exit points for a lock or synchronized block. Notice you can use a profiler, and it sometimes helps, but it might lead you on the wrong path sometimes. Resource starvation is an offshoot of performance issues. Often you would see it as an extreme performance issue that usually only happens when you try to scale. In this case, a resource needed by a thread is always busy and we just can't get to it. For example, we have too many threads and too few database connections, or too few threads and too many incoming web requests. This problem often doesn't need a debugger at all. Your environment usually indicates immediately that it ran out of resources. The problem is almost always plain and obvious. The solution isn't always as clear. You don't want to add too many threads or DB connections to work around the short-term problem. You need to understand why starvation occurred. This can happen because of two different reasons. We sometimes just don't release the resources fast enough, and it ends up catching up to us. You can benchmark and see if something is holding you back. For instance, if I/O is slow or a query takes too long. The second is the more common, a resource leak. We can miss this entirely when running in a GC, garbage collection environment, but in a high throughput environment, the GC might be too slow or for our needs. For instance, a common mistake developers make is opening a file stream which they never close. The GC will do that for us, but it will take longer to do, and the file lock might remain in place, blocking further progress. This is where encapsulation comes in handy. We must encapsulate all of our resource usage, allocation, release, etc. We do that properly, adding logging for allocation, and free should expose such a problem quickly. This is harder to detect with dependency injection frameworks such as String where connections, etc., are injected for you. You can still use some tricks for injected data and resource tracking as well. In the next video, we will discuss the process of elimination. How do we how do we do that? Which areas of the code how do we detect which areas of the code aren't at fault? If you have any questions, please use the Slack channels to ask them. Thank you.